and welcome to our SDG number 14, Life Below Water. We're joined by Will Bateman from CCELL. CCELL is using renewable energy to restore life in our oceans and protect our coastlines at the same time, which sounds like magic. And so I'm really curious how it works, how the story began, and I'm going to pass the mic over to you, Will. Welcome.
Hi, Cameron. Thank you very much. Good afternoon, everybody. I'm Dr. Will Bateman, the founder and CEO of CCELL Renewables. This afternoon, I'm going to talk to you about our work to grow coral reefs, protect the coastline, and as Cameron says, our link into the 5 sustainable development goals that we think we mostly apply to. Just working how to use this. Nope. Next slide. So the main UN goal that we fall under is SDG 14, which relates to life below water. This aims to protect and boost fisheries and other marine ecosystems, along with combating ocean acidification. As you must have heard, coral reefs are at a risk of acidification and are home to nearly 25% of marine life. They are vital to fish populations, and they are a core place where fish eggs settle and juvenile fish grow up. So it's their loss has grave consequences to the rest of the to our way of life. In particular, and what's very relevant of now with COVID-19 is that corals are also very important for the discovery of new medicines. So our work to try to restore some of these is crucial. So how do we do this? I'm going to give you a very quick snapshot here, but we'll come back to this later on. So fundamentally, we aim to take energy out of the waves. We use this to grow rock around a steel structure that we place on the seafloor. This forms a reef, and then we use that reef to protect coastlines from erosion. And the reef also provides corals, which provide this new home for a whole species of marine life. Now, whilst we are super passionate and excited about growing corals and the reefs, our ultimate goal here is to try to replicate the benefits that reefs provide, and our goal is to try to use that for the protection of coastlines. And the reason for this is comparatively straightforward. If you look globally, there is a big issue with coastal erosion. So this is a photo I took last September when I was in Playa del Carmen in eastern Mexico. As you can see from this picture, there is virtually no sand left in front of the hotel, and they're having to resort to some fairly drastic measures to protect the structure. Whilst I was there, we were actually doing some film work, but whilst I was there, I wanted to rent the deck chair, which is shown in, I've circled in red. So I went to reception and asked them, and they presented me with a map. And in my best Spanish, I said I wanted the deck chair next to the water. Okay, they pointed to a square in the middle of this sort of chessboard of deck chairs, and said, this one. I said, no, I want the one on the water. And they said, this is the one on the water. And when you looked at this more carefully, they'd lost about 15 rows of deck chairs over the last couple of years, and that relates to about 30 to 50 meters of sand over this period of time. So, in other words, this is where the beach is now. This is where it was just a few years ago. And you don't have to take my word for it. If you go and look at Google, second photo, come in. If you go and look at Google, the image on the left here is Google's latest photograph that they took back in 2014. And on the right, we've put a drone up and we tried to take the same photograph. And you can see the very, very clear distinction or difference between those two. This threat to settlements is what links us also quite nicely with the Sustainable Development Goals number 11, which is about building sustainable and resilient cities. And it's clear from the erosion that this structure that structures that already exist near the coastline need to be protected. And this is what we're trying to do. But this is not a localized issue for Mexico. So staying with Google, if you type beach erosion into Google, they'll return to you around about 41 million, maybe 500 results in about 0.59 seconds. This is what I did this morning. And if you flip through those images, you flip through to the image search and look at the images, you'll see a page that looks not too dissimilar to this. So coastal erosion is clearly a very big issue globally. You know, anywhere in the world you will find photographs. But coastal erosion in itself is not new. This is something that, you know, a lot of the sand that we see on our coasts is in itself a product of coastal erosion. The white cliffs of Dover in the UK remain white due to steady erosion. So what's going on? Bringing this a little bit closer to home into Europe, this is an interesting illustration of a problem from Duag on the west coast of Ireland. So 35 years ago, they woke up to discover their beach had disappeared overnight during a storm. In May of 2017, it reappeared, also overnight. But sadly, at the start of 2019, it disappeared again following yet another storm. So my point here is storms can instigate huge changes to a beach profile, both good and bad. And they can make these changes happen very, very rapidly. But the amount of sand that we actually see around our coastlines and shores is actually a lot more consistent than you might otherwise think. So the Scilly Isles, which are also within the UK, monitor the amount of sand around their beaches very, very carefully. You know, they're a collection of low-lying islands, and of course, if too much of them erodes, they would cease to exist. So that you can see that they have a very serious vested interest in what's going on. And in the Scilly Isles, they've been monitoring their beaches for many years very carefully, and you can see in this picture here that where they have erosion of sand, which is shown in the red lines, this is often offset by other areas where they've got accretion of sand. So they've got a buildup of sand, which is shown in blue. And over time, if you look at most of these areas, you'll see that they alternate between periods of net erosion and periods of accretion. But overall, I'm told that the volume of sand around the islands remains fairly constant. The real issue is not that we've lost the sand, it's just that the sand isn't where we want it to be. And it's the same pattern that's been repeated globally. So right now, over 70% of coastlines globally are experiencing increased erosion. Beaches, like many things in nature, are a delicate balance between competing forces. Much of the sand, as I've mentioned, is formed from the runoff and sediment and continued erosion, but is predominantly sediment coming off from the land, and it's carried down by rivers. Large grains tend to end up near the shore, whilst silts end up being washed further afield out into the sea. Small waves, as I'm showing in the top right, on the whole tend to be good. They move sand towards the shore, and they help to give the beach its normal profile. Whilst larger waves, which you see sort of plunging breakers, dig away sand from the shore and take it back out to sea. But then you have a number of other factors in play. Wind, for example, blows the sand inland, which is what forms sand dunes, and then you have the currents running along the coastline that can cause continued havoc, moving sand along our beaches. Again, what is crucial to remember is that there is an optimal beach profile in which all of these factors sort of reach an equilibrium. So for example, in Hawaii, we have huge waves, but we also have amazing beaches. So the two can coexist. But when you introduce large waves into a location that has been conditioned for something much smaller, then you start to have a problem, which is exactly what we see in Mexico. So if you want to preserve our beaches, we need to understand the dynamics that went into forming the beaches that we already had. As the Earth warms up due to global warming, the increased temperature that's going into our oceans and also the increase in the air temperature is leading to stronger winds, which in turn leads to larger waves. So over the last 60 years, a very interesting paper was published recently that showed that over the last 60 years, the wave energy has been increasing by about 0.41% per year globally. Whilst this may seem like a fairly small change, cumulatively, this represents a 25% increase over that period. But it's not that. But this is not just an even change across the world. In some areas, we're seeing wave intensity increasing by up to 2.5% annually. And in Playa del Carmen, which I showed earlier, wave energy has increased by about 16% over the last 15 years, so just over 1% per year. And global warming, as you guys probably know, is also driving a number of other factors. So for example, in the last 30 years, there's been a marked 80% increase in the frequency of severe storms. In 2018, it got so bad that hurricanes were practically queuing up to cross the Atlantic. And most recently, we saw the impact of Hurricane Dorian on the Bahamas. And as we enter a new hurricane season, we'll inevitably see a number of category 4 and 5 storms in this coming year. In addition to this, global warming is also causing glaciers to melt, and it's increasing the sea levels. At the moment, sea levels are rising at around about 3.3 millimeters per year, which sounds like, it's not a lot, but that's 10 centimeters in the last 30 years. We can build around that. That's not too much of a problem. The issue is this pace is actually set to increase quite dramatically. So computer models are now predicting that by the end of this century, sea levels will have risen by between 1 and 2.5 meters above what they currently are. And that's based on a 3 degrees C of warming, which I think is the most likely scenario now. If you take that approach or take that sort of view, the statistics are actually quite horrific. So 10% of the population living, globally, 10% of the global population live within 10 meters of the sea. So 10 meters above the sea level. Many cities globally will face major problems. So for example, Osaka in Japan will see an estimated 5.2 million people displaced. In Shanghai, the rise in sea levels will lead to 17.5 million people being displaced, and Miami will be completely submerged. To see what this extra water might look like to the UK, we simply need to actually wind back the clock and look at 1953. So in 1953, the UK seaboard and the Netherlands and parts of Belgium experienced the worst flooding these countries have ever recorded. In the UK, we had around about 300 deaths, and the Netherlands, they had 1,900 people died that night. The event was triggered by a combination of 3 quite unique, well, not unique in themselves, but it was triggered by a unique combination of 3 weather events. First of all, there was a spring high tide that lifted the water up by about 1.1 meters. That just, happens every year, not an issue. On top of this, we had strong winds blowing south across the North Sea, and they not only created large waves, but they also pushed the water in the North Sea up against the land. And this causes this thing people often talk about, it's called storm surge. And finally, there was actually a very low pressure front that was sitting above the North Sea that quite literally sucked up the sea level. The end result that across the eastern side of the UK, the sea levels rose between 1 and 2.5 meters above the predicted high water mark. So that's in addition to the high tide that they had at that time. And that 2.5 meters is somewhat similar to what we've just mentioned in terms of what we expect to see as global sea level rises across the century. Now, that in itself is not necessarily an issue, but it's when you've got this high water level for a coastline that's not necessarily conditioned or used to that, with these very strong waves coming in, where you start to see problems. And this is exactly what happened in the UK. So during that night of 1953, there were multiple catastrophic structural failures of seawalls, embankments, and a reported 1,200 breaches of UK flood defences. Quite simply because the water was higher and the pounding waves were able to just eat away at what little defences there were. Now, the 1953 storm was estimated to be a 1 in 200 year event at that time. It happened in 1953. We haven't had something similar happen. By the middle of this next century, it is expected to occur every 7 years. And that is the horrendous difference in what we're seeing. And to just bring this gain back into a context for those people who live in London, in response to this flooding, London built the Thames Barrier, which is now 36 years old. Originally, they closed it once or twice a year just to test the system and to essentially show it off to the public. It is now closed regularly to actively protect London, with 40% of all closures occurring in the last 10 years, and a quarter of all of those closures occurring in 2014 alone. So, odd years, some quite dramatic things happen. So let's bring this back to what we're aiming to do. So, not entirely, but thankfully nature has a really good solution, and that is coral reefs. So they are a great barrier, and they are a great barrier for one simple reason, that they cause waves to break at sea, so they lose most of their energy in turbulence before they actually reach the land. But crucially, reefs also crucially, reefs only impact the larger waves, with the smaller waves, which I mentioned earlier, which are good, remaining unhindered. So they move towards the shore, and it's that distinction which is what we want to replicate and what we want to take forward. And you don't have to look around in the world much to realize how important the reefs are how important reefs are to the global cities. So 200 million people depend on coral reefs for protection daily. Islands like the Maldives would simply not exist if it wasn't for the reefs around them. And as I've said before, corals are essential to the marine ecosystem and the medicines that we aim to develop and rely on. And as I've gone around the Caribbean, you can see the effect of reefs firsthand. So this, for example, is on the right-hand side are two pictures from Grand Bahamas, and these were taken in 2017, soon after Hurricane Matthew had passed through. Now, the two pictures are actually sequential. So the picture on the top is in the far distance of the picture on the bottom. And what the two pictures show clearly is, as the hurricane came through, in the picture on the top, you saw a huge amount of damage. People lost their gardens, the walls were destroyed, etc. And in the picture on the bottom, everything's great. The only difference between these two locations is that in the picture on the bottom, about 300 to 400 meters out to sea, there is a reef. And it wasn't even a particularly big reef, but it had the effect of just causing those waves, as I said, to break and lose a lot of their energy. Whereas in the top picture, they didn't have any of that same protection. And if you look, again, going back to Google, and you look at what, the coastlines that are around places like Mexico, you'll see that where you see waves, where you see, reefs, so areas where there are reefs, you often find that the land sort of juts out because, again, the waves are coming in, they break, and the land behind it is essentially sheltered. And as I've indicated in red, you can see where there's a break in the reefs, where the land ends up being worn away and is slowly eroded. And it's very sort of common pattern you see all the way along. But as I said, 25% of all coral reefs have been destroyed, and around 60% of those that remain, in fact, are under threat. And in places like the Caribbean, it's even worse than that. We've lost probably 70 to 80% of our coral reefs in that region. So this brings us on to SDG 13, which is, how do we tackle both coastal erosion and the loss of corals? And we're hoping to effectively solve two problems in one with the work that we're doing. Both of these are problems that have been exacerbated by climate change, and they will only increase in intensity over the coming years. So how do we plan to actually combat that? So as I alluded to at the beginning of the presentation, I said, we install these steel structures in the reef, and we effectively aiming to replicate what a coral reef looks like. And through creating that reef, that provides protection to the coastline, and it also provides a habitat. The steel structures are, fairly basic construction grade steel that we put into the sea, and we form it into various dome shapes, and we hook this up to some power, and the electricity that provides that comes in allows us to grow rock around these structures, and over time that rock builds up, providing resilience against the waves, and also, as I mentioned previously, causing them to break and provide that coastal protection. And of course, you've now got this fantastic ecosystem. So what I'm going to do now is just talk through, some of these points. So the core to our technology is really three main pieces. There is, on the one hand, how do we obtain energy, and we do some work around here to obtain energy from the waves themselves. We have some power management, and we need to obviously grow the rock. And I'm going to talk through all of these three things, but in reverse order. So we're going to start with why do we need, how are we growing the rock? The core process is simply electrolysis that you might have seen it in your school laboratory for separating hydrogen and oxygen. So as this photo shows, this is a small demonstration tank that we have in our office, which is probably very similar to what you had in your school lab. At school, you would have filled it with water. You would have connected power across two electrodes, which you would have positioned either end of the tank. You would have put positive power to the anode, and you would have connected to the negative power terminal to the cathode. What you would have then seen are oxygen bubbles rising from the anode on the right and hydrogen bubbles rising off from the cathode on the left. What you would have not seen is the hydrogen plus ions around the anode that actually make the water more acidic, and the hydroxide ions around the cathode that make the water more alkaline, which are crucial to this process. Now, if we take that exact same thing, same system, and you go and put it in the sea is filled with a whole range of other minerals. So things start to become a lot more interesting. So for now, I just want to focus on calcium carbonate, which is what natural coral reefs are predominantly made from. So in this scenario now, where we've got seawater in there, the hydrogen ions that I mentioned earlier, these unseen things, have become really useful because by increasing the acidity in the ocean, they actually dissolve calcium carbonate that's suspended in the water and turn it into a strongly charged calcium ion, which is then attracted towards our cathode. And at the cathode, the hydroxide ion, this is OH minus, actually reverses that whole reaction. So it's now combining the calcium ion with a bicarbonate ion to form calcium carbonate once again, right? I mean, we can go into the more of the chemistry, but that's essentially the simple process. By effectively pumping calcium from one location from around the anode towards the cathode, what we do is we supersaturate the water around the cathode with calcium carbonate. And once that supersaturation happens, the water simply can't maintain that mineral in solution. So it actually starts to crystallize out and form crystals, which forms it around our reef. In other words, we are growing calcium carbonate rock, calcium carbonate crystals, which are otherwise known as limestone rock. And here's it working. So you can see on the bottom here, you can see a piece of rock that's growing, and you can see the little bubbles of hydrogen bubbling off. And you might be wondering about, well, the use of electricity in the sea, and generally speaking, electricity and water don't mix. But you'd be pleased to know that we're using an extremely low voltage. It's only about between 1.23 and about 5 volts. So it has no harmful effect on wildlife. And as you can see, the fish seem reasonably happy. Now, the formation of our reefs is, we're pushing it a bit here, but is loosely connected to two other SDGs. So the first is making sure that our production and consumption processes are responsible as possible. So as an example, we're not yet, but we are moving towards using recycled rebar from construction sites. So we can actually start to recycle a lot of the materials, or reuse recycled materials into what we're developing. And on the left is one of our sponsored natural coral shapes that we add to our reefs. So these are not structural elements. So this is designed to look like a little turtle. But what we're doing is we're adding these onto the outside of the reef to provide sort of randomness to the reef itself. And by making these shapes, it is possible to create more space for fish to grow and thrive, and different protection, and provide different protection to corals as they grow. The shapes also help to provide, additional local sort of labor in terms of people actually manufacturing and even designing them. Then linking also to SDG, so Sustainable Development Goal number 9, so is on the production side. So it's about improving industrial practices wherever we go. As you can appreciate, the standards of health and safety in the UK are higher than that for say Mexico. It's not that the Mexican government has any lower standards. It's just that they are more loosely applied by many of the companies we come across. So we are working very hard with a lot of our suppliers to push forward high standards of safety, ensuring that people have the appropriate protective equipment, apparatus or clothing and even glasses when they're doing the work, and just trying to drive forward better standards across everything that's been done. So in addition to that, we're also doing an awful lot of training in places like Mexico. So for example, one of the main companies we work for in a small town called CD Sugun is now probably one of the few companies in Mexico that can do composite vacuum infusion. That's a process that we use to make the paddle, and we've worked with them and essentially taught them how to do the entire process, and they're now able to not only repeat it for ourselves in terms of making the paddle, but they can also now provide that as a service to other people. And in a similar way, we're looking at ways to enhance welding techniques and drilling techniques and methods for installing the reef. So, okay, moving on from the reef to the middle piece, which is the electronics. So the next part of our puzzle is really about why do we need this piece of, what's this electronics doing? Because this is something that we've invested a huge amount of time in developing here in the UK. And we effectively have 3 main objectives. One is that we need to deliver a very precise current to the reef in order to make it sure the rock that we grow and the speed at which we grow that rock is done in an efficient way, but also we develop strong, healthy, or strong rock. And also when we have corals growing on there, that we also develop strong, healthy corals. So because the 2 are linked. We also need to be able to tolerate a variety of different power supplies. So depending on the sites we go to, we may be using solar, wind, or wave energy, and very often a combination of all of those. So we need something that's very tolerant of varying power supplies. And something that we're also particularly passionate about is about the remote monitoring of these reefs. We want to ensure that they are healthy. We don't want to be, having to swim around them all day long. We want to be able to remotely manage them and understand what's going on, but also start to extract some data from that. So let's look at it very quickly. So I've kind of touched on this already. So what you have here is, we can have multiple different sources of energy coming in, and we have a number of different reef units that we want to power. So we do some clever stuff to match the two between these two. So we ensure that all the time we are actually providing the optimal power to the reef in terms of the current and the voltage we supply, but we're also managing what we're doing in terms of power coming in. So if you think about the wave paddle, for example, the wave conditions are always changing, but more crucially, our wave paddle is moving backwards and forwards. So it's providing pulses of power to our system, which we need to be able to smooth out. Similarly, if you look at a solar panel, the sunlight varies across the day. So clearly at night you have no power. So what do? So what we effectively have is a system that can then mix power from a variety of sources, and we can even link it into the grid. So if you want your reef to grow at the fastest possible rate, we will draw power from the grid during the nighttime, when often power is actually cheapest. And during the daytime, we can actually put power back into the grid to bolster, local supplies if need be, but also smooth out what we're getting from these other sources of renewable energy. Touching on what the output is, as I said, you need to be able to provide an accurate current and voltage to ensure that the electrolysis that we mentioned earlier works correctly. What we're showing here on the right-hand side is what's called the standard reduction tables with the reactions, and I've highlighted the reactions that we're most interested in. So as illustrated, the electrolysis of water, for that to happen, we have to have at least 1.23 volts, which is shown by the top line. Whilst the reactions with calcium ions need a lot more power, but actually it's a negative voltage, which is actually shown at the very bottom line. So it's the voltages we provide here are important. But what you need to understand also is that the sea isn't just made up of one or two of these minerals. It's because it's a big soup of a lot of different bits. And it's therefore crucially important that we provide the right voltages to drive the right chemical reactions, so we get the calcium carbonate, which we predominantly want, in preference to forming other crystals made of other rock, which we know will lead to a weaker rock. And as I alluded to earlier, the final piece of our this big puzzle that we want is we want to get data out of the ocean. It's often said that we know more about the surface of Mars than we do about our oceans. And I honestly don't know if that's really true, but there is certainly a lot more information that we could capture about our seas. And if we have an electrified reef, then by definition, we have power at sea across a long length of our coastline. And this opens up a number of possibilities. So we could collect data at, wave data, for example, at regular intervals along a coastline. So right now, if we were to install a wave measuring pressure probe or something, say every 30 meters, that would be 1,000 times more accurate in terms of spatial density than the current density of wave buoys around the ocean. Now we can have some quite dramatic changes in the available data. We could also install underwater webcams. So something we've been experimenting with is the ability to identify using AI fish and also count them. So we can then measure the overall health of an ecosystem by what we see going past us. We can obviously capture things like the water temperature. Measuring salinity in the area, it's actually a little bit trickier to do, but we are looking at ways in which we can actually measure that and see how that might change across the year. And of course, we can also start to measure pollution levels. So if this could potentially be a means of detecting when there has been an industrial accident or even sabotage where people are releasing pollutants into the sea, we ought to be able to pick it up. So alongside that, as I've mentioned, is come back to the corals. So we're not coral experts. So we have reached out and we're working with a number of teams, but the most prominent one is the Living Reef Foundation in Bermuda. And what they're doing is they're studying with us how the voltage levels impacts the growth of coral colonies. And we're also planning similar projects with teams in Mexico and possibly even in the Bahamas. And to come back to almost like the first part of the puzzle. So how do we create the power? So I've mentioned, we may use solar panels or even connect to the grid, but what we really want to do, given that we've got waves coming in causing erosion, wouldn't it be great if we could use that energy within those waves to grow the reefs to fight back against the waves? So that's the goal. So in this final section, I just really want to talk about how we go about getting energy from the waves. And the first concept I want to be really clear about is that waves are fairly unidirectional in the sense that when you're close to the shore, you see energy coming from out at sea towards the beach. It's rare that you see big waves going from the shore out to sea. In fact, I would not only say it was rare, it's just impossible, okay? You might see smaller ones, but not big waves. So clearly this is a very asymmetric system. So we've got energy at sea moving towards our coastline. And as with many things in nature and in engineering, we have set out to design what we think is, well, so if you've got an asymmetric problem, then invariably you have an asymmetric solution, which as I said, you see in nature and in engineering. So our curved paddle, which is shown in the bottom right, is fundamentally designed to focus the energy towards that's coming in from the sea towards a strong central core, and through its movement backwards and forwards, we then generate power. Now, the crucial feature about our design is this curve. It's unique in terms of what other people are doing within wave energy, but the curvature is almost key to what we've invented. If you think about when you pick up a piece of paper or a pizza, if you bend it, it becomes strong. It's much more rigid. And that's exactly what we've done here. We've effectively taken something that was flat, which is what a lot of other wave energy devices look like, and we've created a curve into that. And what we found is we've managed to reduce the weight of that system by over 80%. And we've also increased the amount of energy we capture by about 2 to 3 times. So we're winning on both sides. And then we link that in with a hydraulic system that turns that into electricity, and then we feed that into our grid. So to give a sense of how long we've been doing this and how we've evolved, we've started from a very simple concept in 2012, where we did some very basic tests in a lab, and we looked at different shapes from curvature, through to sort of 2013 with some more tests in the lab. 2014, we scaled up. We went and got into a very large lab. We were a much larger unit. In 2015, we then did some nearshore tests in Cumbria in the UK with a steel paddle. We soon realized that steel was really not the way to go, because it limited the shape that we could make and what we can do. So we went through a huge relearning process and learning about composites, and then, as I mentioned earlier, we again went out to Mexico, and having taught ourselves and got experts in the UK, we then had to sort of train people in Mexico, and then we started manufacturing the units out there. So the floating design you see here is a lab scale test that we were doing in the UK, and that was followed with a pilot that we built and deployed in Mexico, and we now have three paddles built in Mexico, all waiting to be deployed at the end of this quarter. And I'd like to just add a short note to just, we've been able to do all of this work with the phenomenal support from the EU and the Innovate UK in particular, and also 2 fantastic universities, UCL and Bath University, along with Quality, who are partners in Mexico. So alongside building that paddle, we've also been doing an awful lot of other lab testing, which is illustrated here. So we did some work with the National Physics Laboratory, in which we were running the hydraulic system. So this is the entire hydraulic system and the power generation part of our paddle. And we were testing that in a large tank with NPL to see how it would perform at high temperatures and high load over a sustained period of time. So we were running these tests for about 2 weeks. And overall, so just to sort of step back, as I like to do occasionally, how well have we done in terms of developing a wave energy device compared with what other people were doing? So when we started, there was another company called Aquamarine who had developed an Oyster device. So their stated aim was to deliver 800 kilowatts of power. Our goal is a lot more modest. We're only going for 4. So in other words, we are less than 200 times smaller than what Oyster set out to do. However, when you start to look at the weights and costs, this is where things get really interesting. So their device weighed at least 600 tons. Ours weighs about 220 kilograms. So we are about 2,500 times lighter. And when it comes to cost, theirs, I believe, cost them at least 12 million, where you can buy one from us today for about 6,000. So we have dramatically changed whilst we're small, we have completely changed the cost to weight ratio, and obviously that turns into how much the cost of power is that we generate. And really, to conclude, almost, so this year we have a number of exciting things going on in Mexico. I mean, obviously we've been impacted by COVID-19 like everybody else, but we've managed to actually drive forward. We are hoping to sign a contract with a client this week, and that will be to install the first 100-meter reefs the first of 3 100-meter reefs in Mexico, with 2 more following on in early next year. At the end of this year, we're also aiming to get 3 of our wave paddles back into the ocean. And as I've said, we are also working with these coral hatcheries. So another goal for this year is to start to try to scale up some of the hatcheries in Mexico, so that when we do get these reefs installed, and once we've built up a suitable amount of rock on them, we can actually now start to go out and plant corals. The issue we have at the moment is there aren't enough corals in these hatcheries to be planted onto our reefs. So we need to massively scale up that production. So that's some work we'll be doing. And that, I'm afraid, is me. Any questions?
Oh, I'm afraid that was wonderful, Will. I was never actually that interested, let's say, in science in school, but like you made it very relevant. And also, like I would love. I'm living by the sea right now, and I also want to live off grid. So to have one of these wave catchers, I'm curious how much energy it would generate. Could I run my house with one, or would I need a couple?
No, a house, your average power consumption across a day is probably not more than about 2, maybe 3 kilowatts. So in theory, you might want to have some battery storage in there somewhere, but I think the reality of life is that if you've got if they have got a strong wave environment, yes, you could put one of those in, and you'd probably also want to put solar panels in as well, because typically during the day, people put the air conditioning on, you work during the day, so you tend to use more power during the day. So using solar is actually a very good.
Makes sense.
Makes a lot of sense. And then you use wave to provide the heating sort of during the nighttime, to store up, heat up your water, water tanks, etc., and use it in that way. Remember, wave and what we've developed is not providing a sort of steady 240 volts that you would expect to get out of the grid. We are providing power in sort of pulses, because every time the device moves backwards and forwards, it delivers another sort of pulse of energy.
And just another curiosity about these. What's the name for the wave catcher you created?
We've just called it. Well, interestingly, it started out. So our history, we started out very much around developing the wave paddle. So it was called CCell. Now we rebranded our company recently. So the company is also now CCell. So we now call the wave paddle CCell Wave.
Nice.
Very imaginative.
So the C-cell wave, obviously it would be fantastic to have many of these generating power to create reefs around the world. Are you looking for funding at the moment, or what position are you in?
I think any small company is always looking for more money and funding. We recently completed a crowdfunding campaign, so that closed out at the end of January. So we are, we're reasonably comfortable at the moment for the next year and a half. But depending on how quickly we can get some of these reefs installed, and what we see as happening in terms of the tourism market, I mean, particularly access to places like Mexico, to which we are quite dependent, we possibly might go back to the crowd to look to raise more money in September or October of this year.
Cool. Yeah, I mean, like you said, it's pretty urgent, actually.
Yeah.
I mean, it's an international threat, no one's really safe, whether you're in Shanghai or Sri Lanka. But what has been the international response, would you say?
I mean, I don't, from an international perspective, it's hard to know, because I can answer that actually quite well. So we had a couple of years ago, one of the members of my team went down to Indonesia. We met up with a number of hotels down there, and they were, very interested in about, two aspects. One is to restore their reefs, obviously, and also try to, grow back their beaches. In the one hotel in particular that we were talking to had actually gone out and dynamited a hole in their reef because they wanted to allow boats in and out. Their beach had then suddenly had started to sort of retreat because they clearly didn't understand why it was there, and therefore they were trying to sort of repair that. And in our work with also we've been in a COP a couple of years, and I think for a combination of things there, when Tara was out there, she was sat in on a conference where the Indonesian government were actually advertising our technique, and they were saying, hey, like, there's this company called CSAIL doing this, this sounds like a thing. So I think most people, and particularly at government level, get it. It's the, we know that reefs work, we know that they provide phenomenal protection. It's just what is the cheapest, most cost efficient and environmentally friendly method of rebuilding those, right? And the same is very much true of Mexico. So in Mexico, the government bodies there are increasingly concerned about the way a lot of landowners are trying to protect their coastline, because what they're doing is they're installing effectively large sandbags. They look a little bit like beached whales, right? And they install these along the coastline. They are not good in any way, but there's a number of visually they're not appealing. They also break down over time, etc. Right? So the government there is very keen. They know there's this huge problem of coastal erosion. It has a huge impact on tourism, because if hotels don't have their beaches, people don't go to those hotels. And states like Quintana Roo and the Yucatan, roughly, I've seen conflicting numbers, but somewhere between 80 to 95% of the economy is reliant on tourism.
Yeah.
So right now they're really, really struggling. But as I mentioned in the talk, they've also seen about 70 to 80% of the reefs in the area have also died. So that has knock-on impacts.
Oh, double whammy.
Also for the tourism, also for fishing, and a lot of fishermen in those areas who happen to go further and further afield, etc. So when we've spoken to the governments over there, they are delighted. They really see the benefits of this. What we've needed the crowdfunding for, and what we are doing now is about proving it. So we've got to move from, hey guys, there's a lot of great ideas, to prove it, black and white. Here it is in the water, working, dump. You've saved it. So that's very much our mission over the next. Well, it has been over this year and over this following 18 months, I'd say.
Awesome. One question, actually, at the beginning, you're talking about a lot of the effects that climate change is having on the ocean, and particularly then the effect that the ocean's having on land. But one of the things that I've noticed in my little research is the acidity level of the ocean is rising. And there's quite a correlation with the loss of phytoplankton, which are like kind of the key ingredient to the ocean. And they've also been kind of cut in half in the last 30 years, the numbers. So yeah, I mean, how do you see that possibly affecting your work and what you're trying to accomplish?
So the change in acidity of the ocean is fundamentally the only way we're going to solve that is by people not burning so much CO2, and us finding some inventive ways to try to sort of reverse the damage that we've already done. In terms of what we're doing, we are effectively neutral in terms of the chemistry is neutral in terms of pH. So what you'll find around the anode is the water actually becomes more acidic, but around the cathode it becomes more alkaline, and that's crucial to what we're actually trying to do in terms of the chemistry, because the acidity helps to break down the calcium carbonate in that area, and then it migrates across to the cathode, where the reduction in the acidity actually helps this to crystallize out again. But you also find that reduction in the acidity also helps corals that are placed on the reef to grow, because they're now surrounded by a more waters that are more conducive to what they need to grow. But there's still a lot of work that we need to do in that area. So for example, it's all very well growing these, but what do? Do you provide power forever, or do you turn off the power after 5 years, or what happens? So we're hoping, and there's a lot of good research that's coming out where people have shown that there are corals that will grow in warmer waters. There are corals that can tolerate different levels of sort of acidification, and particularly where places like Bermuda, where they are planting in the research labs in Bermuda, they're growing an awful lot of corals from polyps. So what you're trying to do is you're trying to generate a diverse sort of colony of corals. So a little bit like, not everybody in the world has been impacted by COVID-19. When they get the virus, some people just have a mild flu, other people are in hospital, So if you can create this diverse colony of corals, you'll find that some of those corals will be more resilient to certain environmental effects, be it acidity or temperature or pollution or whatever, and we will know they will lose the others. But it's through that sort of natural selection that we can help. What we're doing with the reefs in two senses. One is that just having the reef in itself, you've got a reef, you've got rock on it, so that's our primary goal. Remember, we want to protect the coastline. But that rock is, I often say, it's a bit like chocolate for the corals. It gives them a fresh white piece of material into which they can attach and they can grow, and they also benefit from the electricity. The question is, as I said earlier, what happens at the end? Do we just suddenly switch the power off, and do the corals all then die, or can we train them to become resilient in their own right? So there's a huge amount of work that we want to do in terms of looking at how we control that power to them. So in a way, if we're giving them the stimulus, we can't. My feeling is we can't just shut it off overnight. We actually have to sort of gradually reduce it, and we need to do an awful lot more research around that to understand that. And again, we will be looking for more money to drive that research.
Yeah. So we're just 5 minutes prior to finishing.
Great.
Okay.
I had a question for you, Will.
Yeah.
A little bit more of a personal one. What was the spark of inspiration or motivation that got you starting CSEL?
So my PhD is actually so when I did my PhD at Imperial, it was actually on modeling extreme ocean waves. And I'm a kite surfer and I'm a kayaker and I do all of those things. Sadly, I don't get in the ocean as often as I like, but I love the ocean, right? I love the water. And I've always been passionate about, who can't be in awe of, when you see surfers coming in on a beach and the power of waves. So in around about 2011, I was feeling a bit bored with the job I had at the time, and wave energy was all the rage. And I actually went for an interview with a company to remain nameless. And I came away and said, I don't think they understand what they're doing. It's kind of a bold statement, but I don't think that's right. So, which is where I touched base with UCL, and I said, look, could you test out a couple of different concepts for me? And they immediately came back. Well, not immediately, but within a few months, they came back. They put in their tank, they put a flat device and they put a curved device, and they immediately came back and said the curved one is moving 40% more than the flat one. So immediately we were like, well,
we're on to something here.
But then the question was, so the spark was really, you asked, the spark was, as I said, I've always had the passion, but the spark was actually just coming away from an interview going, no, I don't believe what they just told me. And sketching up, I actually sketched up something that looked vaguely like our wave paddle on the train down. It looked more like, my fingers here, but it was basically that sort of sketch.
No, I think that is That's so inspiring to hear, but also it's so important for people to hear, because I think sometimes people believe that these solutions have to be formed through really complex periods of thinking and innovating and researching. But it's really refreshing to hear it can just literally be a moment where there's a few of you around the table going, maybe we could do that instead. So it's really, really promising. And I mean, I'm so inspired by the stuff you're doing. I'm glad Cameron asked the question about, are you looking for funding? Because that's definitely something we can connect you guys to. So we'll
Thank you very
definitely
much.
have an
That'd be
offline
great.
conversation on that. But thank you so much. You have really given a lot of people hope for the oceans. So thank you for all the work that you do. And yeah, just keep going. Cameron, did you have any closing thoughts?
No, just supremely inspired and grateful that you shared your time with us. And I'm kind of hoping that one day I can use like a paddle on my board that will also charge my my phone or my camera or something. That would be great.
As an interesting side note, if you there are if you go and look at the racing paddles,
Mm-hmm.
so for people who are doing racing kayaking, and you look at the paddles they use, they also really curved, exactly like our wave paddle.
Nice.
That was another thing I saw a few years later, and I was like, okay, we're not crazy. Because it's just the opposite. You know, they're putting power into the water to try and drive themselves forward. We're just trying to take the energy out. So it links.
Well, I hope you get to spend some more time in the ocean. And yeah, really good
Desperate
job. And good
to
luck.
get back to Mexico and keep pushing things forward there. But we've got a fantastic team out there who are doing things remotely for us. So we haven't been adversely affected by COVID-19 as yet. But it's been good. All right, thank you very much, guys.
Thank you, Will. Thank you,
Keep
Cameron.
on. Thanks, Namisha.
Bye, guys.
See you later.
Okay, take care.